Hi everybody. We are going to talk about spin today. We've just finished talking about the angular momentum, the orbital angular momentum of our electron in our hydrogen atom. So our orbital angular momentum, remember classically we're talking about a radius of our orbit and the linear momentum and taking that cross product. That is looked at as the motion of the center of mass. In our quantum hydrogen example, it's our motion of the electron around the nucleus, and we got spherical harmonics out of that. So that's our extrinsic angular momentum. So that's our first one. And then the second thing we're going to just start looking at here, this is the spin. In classical, it's the motion about the center of mass. So that would be like the rotation of the Earth as opposed to the orbit of the Earth around the sun. In quantum, spin is not described by our position variables. So it's not described by r or theta or phi in our quantum system. So this classical idea kind of breaks down, and that classical comparison kind of breaks down at this point. Spin is what's called intrinsic angular momentum. Because our electron is just a point particle, again, this idea of motion about a center of mass when you're just a point doesn't make much sense. So extrinsic is our orbital, intrinsic is our spin. So the algebraic theory of spin looks just like the algebraic theory of orbital angular momentum in that we can talk about commutators of our different components of spin. So the commutator of the x component with the y component, there is a difference of I, h bar, and our z component. The commutator of our y and our z, we're going to get I, h bar, and our x component. Commutator of our z and our x, we're going to get I, h bar, and y, right? So just like with our orbital angular momentum L that we just did in our previous videos. Just like L, we're going to see that our eigenvectors of our spin squared and a component, so SZ, satisfy similar eigenequations. So here we would write our eigenequation as some equation that is dependent on both an S and an M as our quantum numbers, and we're going to get an eigenvalue out that looks like h bar squared s times the quantity s plus 1, still acting on that same eigenfunction. And let me move myself up a little. And our component sz is also going to have that exact same eigenfunction. So I'm just writing this in slightly different notation this time, but it means the same thing. And it is going to return an eigenvalue of h bar m for that same eigenfunction that is dependent on both s and m. So similarly, let's get to a new page. Similarly, our ladder operators are going to look like either an increasing or a decreasing ladder operator acting on some function s and m is going to give us an h bar times the square root of s plus the times the quantity s plus 1 minus m either plus or minus 1, depending on whether we're using a raising or lowering operator. All of that is under our square root sign. And this is acting on a function that is our eigenfunction of s, and then either m, depending again whether we're raising or lowering, plus or minus 1. So we're going up or down in our quantum number m. So our ladder operators we can compare to our components, and we can say that our ladder operators are related to our x and I times our y component. Right? So our eigenvectors are not the spherical harmonics in this case. That's good to note. Our eigenvectors, not the spherical harmonics, because they are not dependent in spin's case on theta or phi. And remember, the spherical harmonics were functions of both theta and phi. So since they're not the spherical harmonics, we are not limited, and we could include also half integer values for S and M. Awesome. So we can include those half integer values. So that means our allowable values for spin are things like 0, 1/2, 1, 3/2, etc., right? And if we have those values for S, our values for M are going to range from minus S plus 1 through 0 all the way up to our positive S, right? So it turns out that every elementary particle has a specific and immutable value of S. So there is a spin of that particular species of particle. So for instance, you could say that pi mesons, they have spin of 0. Electrons, which are going to be what we're most interested in, they're going to have a spin of 1/2. Photons, also kind of interesting for regular matter and quantum, they're going to have spin of 1. So these are just the immutable values of this. Delta particles have a spin of 3/2. Gravitons, spin 2, and on and on and on. So you can look up tables of elementary particles, and you can get that S is a fixed number, right? It is what it is for any given particle. So S is that fixed number for any given particle. So in contrast, our orbital angular momentum quantum number L could take on any integer value and can and will change from one value to another as the particle and the state evolves. Okay, so we want to talk about electrons that are spin 1/2. So that's where we're headed. So if we want to talk about electrons, we want to look at the particular case where we're looking at S equaling 1/2. So not just electrons, but the spin of particles that make up an ordinary matter like protons and neutrons, also quarks and leptons are going to be spin 1/2. So there are two possible eigenstates for our spin 1/2. So remember, our eigenstates are those things I wrote as SM on the previous pages. So our two eigenstates, S has to be 1/2. So that is true for both of them. And M can either be 1/2 or M can be a negative 1/2. Right? So those are our two eigenstates. When they are both positive, that is something we refer to as being spin up. You could even draw it maybe in chemistry with an up arrow. And if we've got a positive and a negative, we're going to call that spin down. And again, in chemistry, you might have noted that in your orbitals as a down arrow, right? So we're going to use these eigenstates as basis vectors, and we're going to express the general state of a spin 1/2 particle as a 2-element column matrix. So we're expressing the general state of our particle as a 2-column or 2 element, sorry. Let's fix that. So a 2 element column matrix. I didn't even spell column right. So if we're going to express it as a 2 element column matrix, we're going to call that a spinner. All right, so our 2 element column matrix, we're going to use a chi for this. And we're going to call our 2 elements here A and B. What does that mean? That means A is expressing our spin up and B our spin down. And our general state of this particle is a combination of those 2 possible states, right? It could be spin up or spin down. We don't know until we measure. And we have a probability density of measuring one or the other. So we're going to call our spin up part of the spinner, that chi plus, as 1 and 0. And we're going to call our spin down part of the spinner as chi minus, and it will have a 0 and a 1. So if those are our spinners, the spin operators then have to be 2 by 2 matrices. So let's look at that. So our spin operators are 2 by 2 matrices because when we take our spin squared and apply it to each of our spin up or spin down state, we're going to return a eigenvalue of h bar squared s plus 1, still acting on this state. And so our s squared as a 2 by 2 matrix is going to look something like, we'll just use placeholders C, D, E, and F. All right, so C, D, E, and F are going to be our S matrix, or our S squared matrix, and then our S and M, our eigenstates, we've got up here as these 2 things. And our general state is this 2 element column matrix. Whew, okay, so let's keep track of all those things. So our first equation that we're going to look at is going to be for our spin squared. We've got that 2 by 2 matrix, right? So this is our first equation. And we've got our spin up. So our spin up spinner. And because our spin up spinner has to do with a positive 1/2 in both cases, it is going to return an eigenvalue, if m is that positive 1/2, of 3/4 times h bar squared. And that is just me putting in a positive 1/2 in this equation. Oops, lost an s. There we go. Positive 1/2 in that equation. So 1/2 plus 3/2, or times 3/2, is going to give us 3/4 times h bar squared. Okay, so that, and then again, we're going to have, oops, that is, let's fix that. Our first equation, don't want a line in there. So our first equation times our spin up spinner. Okay, then our second equation has to do with our spin down spinner. So our spin down spinner, we've still got C, D, E, and F as our spin matrix. Spin down is that 0 and then 1. Again, it has to do with our negative. Oh, no, I take that back. It has to do with our positive S value, right? S is always positive 1/2. So it has to do with, again, a positive 1/2 in here for S. So that also returns that 3/4 times H bar squared times our spin down spinner. So what we can conclude is that our S squared is going to be equal to this. So that's what our C, D, E, and F are going to equal. Are going to equal 3/4 H bar squared in that kind of identity matrix. So that's easy enough. We've figured out what our spin matrix should be. The next thing we want to do is to look at what our SZ matrix should be. So if I write my equation correctly, we're going to have, acting on our eigenstate S defined by S and M, we should return eigenvalues H bar M, again, acting on that eigenstate S and M. And again, we're going to look at how this acts on our spin up spinner. Since spin up is a positive M, we should get an H bar over 2 acting on our spin up spinner. So that's our first equation there. Our second equation for our Z component should give us that this Z component acting on our spin down spinner should return a negative H bar over 2 acting on our spin down spinner. And so we can find that 2 by 2 matrix for Z, and that 2 by 2 matrix is going to look like H bar over 2 as the component, and 0, 1, or sorry, 1, 0, 0, negative 1. You can do the relations for X and Y as well with this. But the next thing on our list was the ladder operators, right? So our ladder operators look like our up ladder acting on our spin down should return an H bar, and our spin up. Our down, or our up operator acting on our spin up should give us this down and our spin down, and should give us 0. And our down operator acting on our plus should give us H bar and our spin down. Okay, so what does that say? So our up operator should be a matrix that looks like H bar and really has a lot of zeros, but H bar in that upper right corner in row 1, column 2. And our down should be an operator with almost all zeros, but again, H bar in that lower left-hand corner, right? So then our ladder, if we go a little further, we had defined our ladder operator in terms of our components X and Y. So we can say that the X should be 1/2 times, right? We can just do algebra and get to that conclusion. And the y should be 1/2i, so that gets rid of our imaginary term, and the up operator minus the down operator. And so that gets us to the point where we can say that our x operator is h bar over 2 and 0, 1, 1, 0, and our y is going to be this 2 by 2 matrix of h bar over 2, where we've got a 0, a negative I, and 0. Right, so what do we have? We have these two for our x and y, and if I go back up top a little bit, here's the one for our z component. So you can see what these all have in common is that they all have a factor of h bar over 2. In common. So we can write that our spin matrix in general is going to have that factor of h bar over 2, and we can write a sigma, and that sigma can represent as the x component that matrix that is 0, 1, 1, 0. So I'm getting that from right here. I'm going to grab the y component from right here. So the y component of that sigma matrix, we're going to define as 0, negative I, and 0. And the z component, we're going to grab from up top there, that is 1, 0, 0, negative 1. Now, these three things together, or this sigma right here, those are the Pauli spin matrices. So Pauli is in the Pauli exclusion principle. So those are the Pauli spin matrices that let us know how those different components of spin interact. Our factors are different things. The spin squared, the x component, the y component, and the z component are all Hermitian operators. So they're all Hermitian operators. They all represent observables. The ladder operators, plus and minus, are not Hermitian operators. They do not represent something that's observable, right? Okay, so next we're going to talk about eigenspinors of our z component, but I'm going to pause right here so you guys can take a break.